Welcome back to Teen Tutors. We're glad you're joining us. In today's video, we will be covering the last unit of AP Calculus AB, which is applications of integration. So we will be covering accumulation, volume of solids of revolution, as well as the area between two curves. Now, before you start the video, make sure to print out the guided lecture notes in the description so that you can follow along as I teach. Now, without any further ado, let's get into the video. Okay, so let's first discuss accumulation. So when we are given a function for a f of x, right, we can then find the area under a curve using integration. Now, this area under the curve in context can represent the total amount of some value. Okay, so what does this actually mean? So let's say we're given a function that represents the amount of cars per minute that enter a parking lot, right? So let's say c of x equals cars per minute, right? If we would then integrate this cars per minute, right? So the cars per minute. And technically, if you were to draw this on a graph, and let's just say it looks like this, right? Where this would be the cars, C, and M would be our X, right? So then you would have to integrate this with respect to M, right? And dm actually represents the change in minutes. So technically, we can cross these out from a theoretical standpoint, just the units wise, right? So this would equal cars. Okay, so when we integrate this, we're just going to get cars. So what the area under this curve would represent is the total amount of cars that have entered the parking lot. So we're going to have questions like this. It is almost guaranteed that you are going to have an FRQ on accumulation, okay? So in this question, we're asked the rate in hundreds of people per minute at which people are entering a concert is P of t equals 20 minus 5t squared. Then we're asked how many people have entered the arena in the first 6 minutes. So here what we're going to do is we're going to take the integral from 0 to 6 of this rate, right? So when we integrate the people per minute, we're just going to get people. And then so we would have our answer in people, right? So we're going to do 20 minus 1/2 t squared dt. We're going to get 20t minus 1/6 t cubed, evaluated from 0 to 6. And this is then going to equal 120 minus 6 cubed over 6 would be 36. And then minus, we would just get 0. So this is going to give us 84, but keep in mind that it's telling us in hundreds of people per minute, so it's going to be 8,400, right? So our answer here would be 8,400 people, right? So now we're asked, people are now leaving the arena at a rate of L of t equals 32 minus t squared in hundreds of people per minute. And then we're asked if there were 12,000 people in the arena, how many people are still inside after 3 minutes? So in this question, again, all we have to do is take the integral. From here, it's going to be 0 to 3 of 32 minus t squared dt. Because if you integrate the people per minute, you're just going to get people, right? So this would give us 32t minus 1/3 t cubed, evaluated from 0 to 3. So we're just going to get 32 times 3 minus, we would get minus 9, which is going to give us 87. Okay, and then remember, again, you need to make that 8,700. However, it's telling us that what's happening is that is how many people have left, right? So it says if there were 12,000 people in the arena at the beginning, how many are still inside? Well, then we would just do 12,000 minus 8,700, and we're going to get 3,300 people. So our answer there would be 3,300 people, right? So let's now talk about displacement. So we talked in earlier units when we're differentiating that we can go from position to velocity to acceleration using differentiation. We can do the same with velocity, acceleration, and speed, and as well as distance, right? And we can use integration to get from the acceleration to velocity and then from the velocity to the distance. And we would usually do that when we're evaluating differential equations. But here, if we are asked for the displacement, which is the change in position from time t equals a to t equals b, we would then just integrate v of t, okay? So if we're just given v of t, then we can find the displacement using that integral. Now, if we want the distance traveled, because these are two different values, we need to absolute value v of t. So how are these different values? Well, let's just say that if I go up 5, and then I come down 2, right? My net change, right? And I shouldn't draw an arrow there. Let me draw it as an equal sign. My net change will be plus 3. However, my total distance, right? This would be displacement, right? So this would be displacement. And then what would my total distance be? Well, my total distance would just be 7, okay, in either direction, right? No matter how far I went, let's say it's 5 steps and 2 steps. Even if I did 5 steps and turned around and then took 2 steps, in total I took 7 steps, right? So that would be the distance. So here we're asked, a particle moves along in axis with a velocity modeled by t cubed minus 6t squared plus 4t, where t is in seconds and v of t is in centimeters per second. We're then asked, how far does the particle travel between t equals 3 and t equals 6? So here all we need to do is we need to evaluate it from 3 to 6 of t cubed minus 6t squared plus 4t dt. And so we would put that into a calculator, and we are actually just going to get 39.9 or 36.972. Now keep in mind, we have to have that absolute value because we're asked how far does it travel, not the displacement. We are asked how far does it travel in total. Okay, now we are asked what is the displacement, right? And I should put cm here. So what is the displacement? Well, that's just going to be the integral from 3 to 6 of t cubed minus 6t squared plus 4t without the absolute value, because now we're asked for displacement. And if you then put this into a calculator, you're going to get negative 20.25 centimeters. So what you see is these are two different values, okay? You need to make sure that you're being careful. Something to note is if the function changes from positive to negative on the interval, you need to set it up into two different integrals. So let's just say that we had a function of, let's say we had, I don't know, x squared minus 3x minus 4, right? And we were going to evaluate from, let's say, 0. Well, let me factor it so I can decide what we're going to do. So we would have x minus 4 and then x plus 1, right? So let's just say from 0 to x to 5. Okay, so this value at x equals 4 is going to change from positive to negative. So we would have to evaluate this as the integral from 0 to 4 if we're trying to find the total distance of x squared minus 3x minus 4 dx plus the integral from 4 to 5 of absolute value of x squared minus 3x minus 4. So just be careful. They will definitely try to catch you off guard, and you are going to have to make sure that you check if the interval changes from positive to negative, or if the value changes from positive to negative on the interval. Now, before we start talking about the area between two curves, a staggering 98% of viewers to this channel are not subscribed. So make sure that if you find videos like this one helpful, you subscribe to the channel so that you don't miss out on our future FRQ as well as multiple choice review, so that we can help you prepare for the AP exam. Okay, so let's now talk about the area between two curves. So given the functions f of x and g of x, where f of x is greater than g of x on the interval I, the area between these two curves will be the area equals the integral from a to b of f of x minus g of x. So this is just a fancy way of saying if we want to find the area between two curves, and let's call this f of x and let's call this g of x, we would take the top integral, so we're going to evaluate it from a to b. We would take the top integral f of x and we would subtract g of x, and we would do dx. Okay, now not yet, but what we're also going to have to do in these problems is actually evaluate the interval where they are going to be enclosed. Okay, and so here would be the type of question where they would ask, what is the area of the region enclosed by these graphs? But we could also just look at it as two graphs. So here we're asked to find the area between the functions y equals 2x and y equals 3x cubed plus 4 from x equals 2 to x equals 4. And let me actually change this to a 2. It's going to make the integration a little bit easier if I'm looking forward, right? And so if we want to find this area, first let's draw these two graphs and see which one would be above the other, right? So the 3x squared plus 4 is going to look something like this, right? And then the 2x is going to look something like this. So then how would we find the area between these functions from 2 to 4, right? Well, we would literally just evaluate the integral of the top minus the bottom. You can look at this as just top minus bottom, okay? And so here all we have to do is the integral from 2 to 4 of 3x squared plus 4 minus 2x dx. And so we're going to get x cubed plus 4x minus x squared evaluated from 2 to 4. So we would get, it looks like 64 plus 16 minus 16, and then minus we would have 8 plus 8 minus 4, right? And that would end up giving us 64 minus 12, which is going to be 52. Okay, now another example. Find the area between the functions f of x equals x squared plus 5 and g of x equals x squared minus 4x from x equals 0 to x equals 3. So in this question, again, let's draw it. So x squared plus 5 would look something like this. Okay, and then x squared minus 4x is going to look something like this. Okay, and so from 0 to 5, it looks like the x squared plus 5 is always going to be on top, or from x equals 0 to 3, right? And let's just draw it here. Okay, it might be a little off, but it doesn't really matter. So how would we draw this? Well, we would do the integral from 0 to 3 of x squared plus 5 minus x squared, and then plus 4x, because if we subtract a negative 4x, it'll be plus dx. So it looks like these x squareds will cancel. We'll just have the integral from 0 to 3 of 5 plus 4x dx. And then this is a pretty easy integral. We'd get 5x plus 2x squared evaluated from 0 to 3. And then if we plug in our 3 and 0, it's just going to be looks like 15 plus 18, and then minus 0. So you would get 33. All right, so let's look at a couple more examples. So now we want to find the area bounded by graphs. Okay, so this is what I was talking about earlier, where we're going to have to find the actual interval where these two are contained. Okay, so here, let's draw x cubed and x, right? So if we draw this, this would look something like this. So our x cubed is going to look like this, and our x then is going to look like this. Okay, and so if we zoom in, the x is going to be our bottom graph here, and the x cubed will be our top graph here. However, after x equals 0, our x will be our top graph, and our x cubed will be our bottom graph. Okay, so here we are going to have the integral here from -1 to 0 of, because our top graph here is going to be x cubed, so x cubed minus x dx, and then plus from 0 to 1, our graph is going to be x minus x cubed dx. Okay, so we could set this up as, since both of these intervals, if I were to zoom in on this, it would look like this. So, and then, okay, both of these intervals have the same area, okay, just because they're the same function, but one of them is negative, so they have the same area. Okay, so I can just make this 2 times the integral, let's just say from 0 to 1 of x minus x cubed dx. I'll take this one. It's a little easier because there's positive bounds. So let's call this 2 times 1/2 x squared minus 1/4 x cubed dx, or not dx. Now we're going to evaluate it. So 2 times 1/2 x squared minus 1/4 x to the 4th, evaluated from 0 to 1. So then we would just have 2 times 1/2 minus 1/4, which would give us 2 times 1/4, or 1/2. Okay, so now we're asked to find the area bounded between f of x equals square root x, g of x equals 6 minus x, and y equals 0. So first, let's draw this. So f of x equals square root x is going to look like this. Then we would have g of x equaling 6 minus x, so that's going to look something like this, right? And then we want it to be bounded by y equals 0. Okay, so it looks like it's going to be this whole area, right? So what we could do actually is we could just break this up into these two halves, let's say, okay, and find these integrals separately, and then it would just be a single integral. It wouldn't even be the area between two curves. It would just be, okay, well, what's the integral from here to here, right? And then we could say, okay, well, then what would be the integral from here to here, right? And so we would use 2 different functions, obviously. So it looks like until these meet, they will have root x, and then after they meet, we'll have 6 minus x. So let's find when they meet, right? So we can say that root x equals 6 minus x. So we can say that x equals 36 minus 12x plus x squared. And then we could say that x squared minus 13x plus 36 equals 0, right? So we could factor this into x minus 4 times x minus 9 equals 0. And then we could say x equals 4 or 9. Now, obviously, this is not going to be 9. And why is that? Well, because if x was 9, then our g of x would be -3. So it looks like it's going to be 4. Okay, so we're going to have the integral then from 0 to 4 of the square root x dx plus the integral from 4, and then 4 to what? Well, when do we touch the y-axis? That will be when g of x is equal to 6. So from 4 to 6 of 6 minus x dx. Okay, so then we would just have, this looks like it's going to be what? So we'll have x to the 3 halves. So 2/3 x to the 3 halves from 0 to 4. And then plus, we'd have 6x minus 1/2 x squared from 4 to 6. Right? And so this would give us 2/3 times 4 to the 3 halves is going to be 4 root 4, which is 8. And then plus we would have here 36 minus 18. And then minus, we would have 24 minus, 8, right? So we would get 2/3, we would get 16/3 plus 2. And that would give us 22/3. Right, then finally we're asked to find the area of the region bounded by the graphs y equals plus or minus square root of 3 minus x. And then we would have x equals y plus 1. So what would this graph look like? Well, this graph is going to look like the following. So we're going to have a graph that looks like this. Okay, so that's going to be y equals plus or minus square root of 3 minus x. And then what is x equals y plus 1? Well, that's just y equals x minus 1. So it looks something like this, right? And so let's find when they touch. And let me actually not draw it like that because they don't touch here. So let's just draw it like this. All right. And so first, we need to get this in terms of x. And why is that? Well, instead of doing top minus bottom, we can also do right minus left. Okay, so we actually could have employed this strategy here. It was just easier to do it the way I did it. Now, how do we do right minus left? So we're going to find the, instead of doing top minus bottom, we'll do right minus left, right? Because this is the area we're trying to find. Okay, so how do we actually employ this? Well, we need to get this in terms of x, and our bounds will then be y. Okay, so if we square root both sides here, we could say y squared equals 3 minus x. So we could say x equals 3 minus y squared. And then here we already have it in terms of x. So our right function is going to be 3 minus y squared, and our left function is going to be x minus 1, right? So now we just have to find when they're equal to each other, right? So we would have to find when 3 minus y squared is equal to y plus 1. So we would have that y squared. So y squared plus y minus 2 is equal to 0. So it looks like we're going to have y plus 2 and y minus 1, right? So y plus 2 and y minus 1 equals 0. So it looks like y is going to equal 1 and negative 2. So we're going to have the integral from negative 2 to 1 of 3 minus y squared minus y plus 1, right? And I'm actually not going to solve this integral. We're just going to set it up here because it's kind of redundant to solve it again. It's the same type of thing, except now you're just integrating with a y. Okay, so now let's briefly talk about average value. We're actually not going to give an example of this because it's very, very simple. You just need to know the formula. So for a function defined on any interval I, we can find the average value of the function by writing that the average value will equal 1 over b minus a times the integral from a to b of f of x dx. So what does this look like? Well, let's say we have this function f of x, and we want to find the average value from a to b. All we would do is we would find what is b minus a. So let's say this was 1 and this was 3, right? So we would have 1 over, what's 3 minus 1? It's 2, times the integral from 1 to 3 of f of x dx. So that's really all we have to do. It's literally what is the integral from a to b, except now we have to do 1 over the top minus bottom bound. Okay, so let's now talk about volume of solid of revolution. So while this might be one of the most challenging AP calculus topics you'll learn, maybe even challenging calculus topics you'll ever learn, in my opinion, it is very unlikely that you'll see a lot of these questions on the AP exam. So try to really understand the volume of solids of revolution about the x-axis, the volume of solid of revolution about the y-axis, and then just understand a little bit about the washer method. We're going to get into talking about these, but don't beat yourself up over not truly understanding these. If you do, that's obviously wonderful, but you're probably only going to see 1 to 3 questions of this on the AP exam, and most likely you will not see this on an FRQ. Okay, So we are asked to find the volume of a solid here that is created by revolving y equals x squared from x equals 0 to x equals 1 about the x-axis. So basically, if we're asked for the volume that is created by revolving a function, and that function is defined by x, not by y, right? We can just write that it's going to be pi times the integral from a to b of r of x squared dx. So literally all we have to do here is if we draw this function, y equals x squared, it would look like this. And from 0 to 1, right? So this is 0 and this is 1. Right, we would just write pi times the integral from 0 to 1 of x squared dx. So we would just have pi times the integral from 0 to 1 of x to the 4th dx, which would equal pi times 1/5 x to the 5th, evaluated from 0 to 1. So it's just going to be pi over 5, or you could write 1 over 5 times pi. Okay. So next we're asked to find the volume of the bowl-shaped solid that is created when you revolve the area bounded by y equals 1 plus root x, x equals 0, x equals 4, and y equals 0 around the x-axis. So again, all we need to do here is let's draw it. So what does 1 plus root x look like? It looks like this. And let's actually draw that a little better. So it looks more like this. And then what is our bound? So we're going to be bounded from x equals 0 to x equals 4. And then by y equals 0 as well. So it's going to be this, right? And then we're going to revolve this around the x-axis. So our actual volume would look like this, and then it would be in 3D, obviously. Okay, so what would we do here? Well, we would just write pi times the integral from 0 to 4. Those are our x bounds of the square root of x plus 1 squared dx. And so we would have pi times the integral from 0 to 4 of, we would then get x plus 2 root x plus 1 dx. So it looks like we're going to get pi times 1/2 x squared plus, this would be x to the 3/2, so we'd get 4/3, and then plus x. That's going to all be evaluated from 0 to 4. So we're going to get pi times, it looks like you'll have 8. So 8 plus, looks like you're going to have 32 over 3. And then you're going to have plus a 4. And then you're just going to have minus a 0, right? So this is going to equal, we're going to get pi times 12 plus 32 over 3, which is going to give us 68 pi over 3. Okay, so let's take a look at what happens when we now have volume of solids of revolutions, and this should say about the y-axis. Okay, so what are we going to do here? Well, to find the volume that is created when we revolve around the y-axis, and I forgot to put the y-axis there, right? How would we find that volume? Well, it's going to be the same exact formula, but now we're just in terms of y. So here we're asked, find the volume of a solid that is created when you revolve the area enclosed by x equals square root 1 minus y, y equals 0, and x equals 0 about the x-axis. So let's draw this. It's a little easier to think about this in terms of y. So let's actually rewrite the equation in terms of y just to draw it graphically. So we have x squared equals 1 minus y. So y equals 1 minus x squared. So now we'll actually understand how to draw this. So it would look something like this. Okay. However, when we're integrating, we're going to be using this. Okay. So what are our bounds? Well, we're bounded by y equals 0 and x equals 0, right? So we're here. Okay. So what are our bounds? Well, now instead of our bounds being determined by x, they're going to be determined by y. So what does our y go up to here? Well, if our x is 0, which is where our y is at its max, then y has to equal 1, right? Because 1 minus 1 would equal 0. So we're going to have the integral from 0 to 1, and we'd have a pi on the outside, times square root 1 minus y squared dy. So we're just going to have pi times the integral from 0 to 1 of 1 minus y. So it's just going to be pi times, and we should have a dy, pi times y minus 1/2 y squared, evaluated from 0 to 1. So it's going to be pi times 1 minus 1/2 minus 0. So it's just going to be 1/2 pi, which equals pi over 2. You could write it either way. Okay, so now let's talk about the washer method. So this is where a lot of people get a little bit confused. So if we are trying to find the volume, but it is between two curves, okay, we are going to use the washer method. So when we found the area between two curves, we did f of x minus g of x. Now we're going to do r of x squared minus r of x squared dx. Okay, so let's just take a look at some examples. So find the volume of the solid that is created by revolving y equals x squared and y equals square root x about the x-axis. So how would we solve this? Well, if r equals square root x, right, we're revolving about the x-axis, so we don't have to worry about anything really else. You'll see when we're revolving about things other than the y, the x or y axis is a little bit more challenging, right? So let's first draw this actually. So r equals, or y equals x squared will look like this, right? And then y equals square root x will look like this, right? So we're going to be looking at this area. So what is the big radius? Well, the big radius, either radius actually, is the distance from that function to the axis we're revolving about. So here, our big radius would just be, it looks like it's going to be square root x, right? Because we're evaluating it from this part, right? So we're evaluating this part of the curve. Okay, and then for the x squared, right, that's going to be our little r, right? So that's going to be our little r, this will be our big R. So how are we going to write this? Well, we're going to write this as volume equals pi times the integral from what to what? Well, when does x squared equal root x? That's going to be at 1, so it's going to be 0 to 1. We would then have the square root of x squared, so just x, and then minus an x to the fourth dx. Okay, so this would be pi times, we can just integrate this now. So we'll have 1/2 x squared minus 1/5 x to the fifth at 0 to 1. So we're going to have pi times 1/2 minus 1/5 minus 0, right? So that's going to give us, looks like that would be 3 pi over 10. So let's look at some more examples. Find the volume of the solid that is created by revolving y equals x cubed and y equals x about the x-axis. Okay, so for this question, we could just write this as, okay, well, it looks like our x cubed is going to look like this, and then our absolute value of x is going to look like this. Okay, so here, since we're revolving these points where they're equal, so if I zoom in, it'll look like this. Since I'm revolving around these points where they're, or bounded by these points where they're equal, I can just write this as y equals x, because y equals absolute value of x and y equals x are the same if x is greater than 0, and it is here. So this is going to be the integral from 0 to 1, because that's when absolute value of x and x cubed equal each other, of x squared, because again we're using this function, and we could just model it as x instead of absolute value of x, minus x to the 6th, that would be x cubed squared, right? And we have to have a pi out here, times dx. So we would have pi times 1/3 x cubed minus 1/7 x to the 7 from 0 to 1. So we're going to have pi times 1/3 minus 1/7 and then minus 0, which is going to give us 4 pi over 21. Okay, so in this question, we're asked to find the volume of the solid that is created by revolving the area enclosed by y equals square root x, x equals 0, and x equals 4 around the line y equals 4. So let's draw this. So we have the lines for, let's say, we have the lines for square root x, which would look like this, the lines for y equals 4, which would look like this, and we're revolving around the line x equals, or we're revolving around the line y equals 4, and then we also have x equals 4 here, so let's just draw it like this. Okay, and so this area is the enclosed area, right? So then we can say, okay, well, what is our little r? Well, we're revolving around this line, so our little r looks like it would be this, right? And then our big R is going to be this, right? So our big R is just going to be 4, okay? And our little r is going to equal 4 minus the square root of x, okay? So what we're going to have is we're going to have pi times the integral from, we would have 0 to 4, because that's where these are bounded by, of, we would have 4 squared minus 4 minus root x squared dx. And I'm going to save time by not actually evaluating this, but that's how you would set that up. Okay, and so let's take a look at another one. We're asked to find the volume of the solid that is created when you revolve the area enclosed by y equals square root x, x equals 0, and x equals 4 around the line x equals -1. So here, if we drew this, well, so we have our y equals square root x, that would look like this. we have our x equals 4, that would look like this. And we are revolving around the line x equals -1. So what we're going to have to do is we're going to have to actually get this into terms of y, or into terms of x equals y. So instead of y equals in terms of x, we're going to have x equals something in terms of y. And why is that? Well, when we are revolving parallel to the y-axis, we need to get it into terms of y. When we're revolving parallel to the x-axis, as we are here, we would keep it in terms of x. So here I'm going to say that x, so we say y squared equals x, right? And so what is our big R? Well, our big R is just going to be this distance, right? And our little r is just going to be this distance, okay? So we could say that big R is just going to equal 5, right? That's the distance from 4 to -1. And then what is our little r? Well, that's going to equal right minus left. So it's going to equal y squared minus -1, which will equal y squared plus 1. So we would set this up as v equals pi times the integral from, what would our bounds be? Well, now our bounds are in terms of y, okay? So what do our y range from? Well, it ranges from 0 to here. If x equals 4, then y equals 2. Why? Because the square root of 4 is 2, right? So we could say v equals pi times the integral from 0 to 2 of, we would then have big R, so 5 squared, minus, we would then have y squared plus 1 squared dy. And again, I'm not going to evaluate this integral because it's just repetitive, okay? And also, a lot of the times, especially if you see a volume question on an FRQ, they probably won't ask you to evaluate an integral like this. They would usually tell you to set up the integral for it, and then you wouldn't actually have to evaluate it. And even if we did again, it's just redundant. Okay, so let's now talk about the volume of cross sections. So if we're told that we have cross sections, what we need to do is we need to write that our volume would be the integral from a to b of a of x dx or a of y dy. Okay, so let's actually just talk about this instead of going through notation. So we're told to find the volume whose base is bounded by x squared plus y squared equals 4, and the cross sections perpendicular to the x-axis are squares. So first of all, what does this look like? It looks like this, right? And the cross sections perpendicular to the x-axis, so it would look like perpendicular to the x-axis would look like this, and those are squares. So it's hard to draw this in 3D, but if we went up, they would be squares. So like these would all be squares, okay? So what we're going to do is, well, what is the area of a square? Well, it's a equals x squared, right? We're not given any bounds for our x, so it's just going to range from -2 to 2, because that's what our x is going to range for this circle, right? And so let's get this in terms of y. So we could say y squared equals 4 minus x squared, so y equals the square root of 4 minus x squared. And so we need to be careful because this is only going to give us the top half. So I'm just going to take this integral and multiply it by 2, okay? That way we can say that, okay, we also have this bottom that just adds here, right? So we're going to write this as the volume equals the integral from -2 to 2 of 2 root 4 minus x squared, and then we have to square it. Why? Because we can think of our x as our f of x, okay? Again, or a of x. We could just write this as f of x, right? So we would then write that the volume, and we should have a dx here, so we could then write that the volume is going to equal 4 times 4 minus x squared. It's going to be the integral from -2 to 2 of 4 times 4 minus x squared dx. So we'd have that the volume equals the integral from -2 to 2 of 16 minus 4x squared dx. Right, so then let's evaluate this. We're going to have 16x minus 4x cubed over 3 evaluated from -2 to 2. And so this is going to give us 32 minus 32 over 3. And then minus, we would have -32 plus 32 over 3. So it looks like we're going to get 64 minus 64 over 3. This is just going to give us 128 over 3. And notice we could have just evaluated this integral by itself and then multiplied the 2 at the end, because if you look here, if we had just evaluated this one integral and just multiplied it by 2, we would have gotten the same thing. So that could have potentially also worked, but just made more sense to put that 2 in front at the beginning. Okay, so let's now look at this last question. So we're given y equals 4/3 x minus 3, and we're asked to write the integral for the volume if the cross sections perpendicular to the y-axis of a right triangle are semicircles. So let's just draw this first. And so we're going to have a function that looks like this, right? This would be the point of 4, 0. This is going to be the point of 0, 3. Okay, and it says that the cross sections perpendicular to the y-axis are semicircles. Okay, so if we are perpendicular to the y-axis, we need to get this in terms of x equals something in terms of y. So we can say that x, so y plus 3 equals 4/3 x. So we could say 4/3 y plus, we would say 4/3 y plus 9/4 equals x, right? And so what does this represent? This just represents our x in terms of y, so if we were going out this way, right? So what we're going to do is our radius is going to be 1/2 times, we would have our, and this should be 3/4, not 4/3. So 3/4 y plus 9/4, and we can attribute that to the fact that it is a triangle, right? And so we would then have, this is equal to 3/8 y plus 9/8, right? And so what is the area of a semicircle, right? That is 1/2 pi r squared, right? So this is our r, okay? So how would we solve this? Well, we would just do the volume equals the integral from, what are our bounds? Well, if we are now in terms of y, then our bounds are also in terms of y. So it's going to be -3 to 0. So -3 to 0 of 1/2 pi times 3/8 y plus 9/8 squared, and then dy.